Okay. So if we're wanting to define a transformation of a position vector, well, one of the things we can do, which is what we're going to want to do, is we can say, oops, better not do it there, a translation can be defined as some vector p plus, well, I'll say, let me do this. I'll say it's some vector q described in A plus p described in A, which points at B. No, this isn't quite right. Give me a second. So if we have a vector described in B and we want to describe it in A, so let's say that we have this vector described in B that is 2, 7, 4. I know that probably isn't right. And our translation vector, or our position vector, pointing to frame B from A is 1, 9, 7. Then we can say that the translation of the vector from frame B to frame A is, so P, the position of the vector in A is going to equal the position in B plus the position vector of the origin of B described in A. So what we have here then is we have 2, 7, 4 plus 1, 9, 7 gives us the vector described in A. So in this case we would have 3, 16, 11. So ultimately what we'd be doing is describing the vector from the origin of A instead of from the origin of B. That makes sense? Another way of doing this is to define a transformation matrix. Rather than very literally adding these together, we could develop a transformation, and let me show you what that would look like. This will be the setup for our homogeneous transformation that I don't think we're going to get to today. So, okay, keep in mind that we've already touched on what this homogeneous transformation is going to look like. It will look something like this, where we have a rotation matrix followed by a position vector, a bunch of zeros here, and a 1 hanging out here. If we're not rotating frame B with respect to A, then what are we going to populate this first portion of the matrix with? In this case, what we're wanting to do is define only a translation matrix. That means that there will be no rotation taking place, so
Just zeros?
the identity. Okay, because we don't want this part of the matrix to do anything at all for us. So we're wanting to just go through and leave the rotation alone. And we do that by filling the upper minor with the identity. And then up here we have our, in this case, our position vector pointing from frame A to the origin of B. So that will be our 197. And then we have a 1 in the lower left, or lower right-hand corner. So check this out. When we go through and take that translation, transformation, we can take that 1, 0, 0, 1, 0, 1, 0, 9, 0, 0, 1, 7, 0, 0, 0, 1, multiply it by the vector in B. We have to include a 1 here so that our dimensionality is the same. So 2, 7, 4, 1. And when we do so, we have 1 times 2 is 2, plus 0 plus 0 plus 1. So we end up with a 3. We have 0 times 2, 7, 0, 9. So 7 plus 9 is 16. 0 plus 0 plus 4 plus 7 is 11. And then 0 plus 0 plus 0 plus 1. Right there is our vector expressed in A. So that's why these homogeneous transformations are so very nice, because they're much more compact than doing all of this, all of these translations out manually. They allow us to condense all of the information into a single package, both the rotation and the translation vectors, and it just saves a ton of space. Now, as I've mentioned already, the program is going to run more efficiently if we work in 3 dimensions rather than 4 dimensions like this. But ultimately, last time I taught this class, I set up everything in 4 dimensions, and it's still, our computers aren't powerful enough to handle it. So really the choice is yours. You have the option of either setting this up in 3 dimensions, make it more efficient, or 4 dimensions to make it easier to interpret. So, okay, and with that, let's stick a fork in it today. Tomorrow when we come back, we'll go on into looking at the rotation, transformation, and then merging these two together in order to come up with a complete homogeneous transformation that we'll be working with the rest of the quarter. So.